So good evening, everybody. It's not rocket science, but as you can see from the subtitle, well, really it is. But we're going to try and do a little bit of rocket science, but basically leave the maths behind. So where should we start?
What do you do?
Why, I don't mean to boast, but I'm a brain surgeon.
Brain surgery? Not exactly rocket science, is it?
That's the phrase, it's not exactly rocket science, implying that rocket science must be difficult. But I'm not talking about these things specifically. I'm not talking about rocket engineering or rocket technology, how we build something as awesome as a Saturn V. It's about how we get around the solar system, how we get from one orbit to another, for instance. So I'll be talking about what rockets do. I'll be talking about orbits as observed by Kepler and explained by Newton. I'll be talking about how we get from one orbit to another, for instance, how we go from Earth's orbit to Mars' orbit, and also how we explore the outer parts of the solar system. And I'll finish with that odd concept of how can we possibly park a spacecraft at nowhere in particular, a weird place called a Lagrangian point. If there's nothing there, how can we put a spacecraft in orbit around it? So, is rocket science complicated? Well, I like this quote. It might seem very complicated at first, but when you keep digging deeper, you'll soon realise it's even more complicated. And usually that's because the maths gets in the way. So let's make a start. Let's think about rockets themselves. What does a rocket do? If we ask the man in the street, what's the primary function of a rocket? You'll often get the answer that something like it's designed to lift objects above the atmosphere or get from the Earth into space. Well, that's sort of half of the answer. It is sort of the job of a rocket to lift things up above the atmosphere. But bear in mind that, for instance, the International Space Station and the Hubble Space Telescope are actually still inside the Earth's atmosphere. It's just rather thin up there at an altitude of order 500 kilometers. So to put an object into Earth orbit, what you need is not vertical velocity. That's not the function of a rocket. The function of a rocket is to give the spacecraft horizontal velocity, horizontal in the conventional sense of parallel to the horizon, and that will put you in an orbit around the Earth and ultimately allow you to leave the Earth and go elsewhere in the solar system. Getting as high as possible to reduce atmospheric drag, well, that's probably a good idea, but strictly speaking, it's not necessary in order to orbit the Earth to gain height. You can, in principle, orbit the Earth at a relatively low height if you wanted to. So, this has been known for a long time. For instance, in Newton's Principia, dating back to the 1686, he had this diagram which is blown up on the right-hand side as more of a cartoon there. What if you were to put a cannon on top of a mountain and fire a cannonball horizontally? Well, it's the horizontal velocity that determines whether or not you go into orbit. This was understood by Newton, written down, and that's been a staple of orbital mechanics ever since. So we can ask ourselves, what would happen if we fire a cannonball at a low velocity? Well, the answer is it would fall to Earth, as indicated by trajectory A. And if we fire it faster, then it will go further, so it might fall to Earth as indicated by trajectory landing at B. The point is, if we fire it fast enough, it can go all the way around the Earth and basically come back to where it started from. So the horizontal velocity dictates whether or not you're going to go into orbit. And Newton understood that hypothetically, if we were to try this from a planet with a much stronger gravity, even at the same height above the sea level, even at the same radius of planet, if gravity was stronger, then we'd have to fire the cannonball faster in order to achieve orbit. The stronger the gravitational pull, the faster we'll have to kick out the cannonball. So why this misconception that the only purpose of a rocket is to go vertically up? Well, that's because that's what you see when they launch. Initially, the rocket is moving vertically. but it isn't too long before it starts tilting over, because its main job is to increase the horizontal velocity of the craft it's trying to put into orbit. So that tilt of the Saturn V there, that's not an accident of perspective, that is a genuine tilt of the rocket which starts fairly soon after liftoff in order to start building up the horizontal velocity. If you were not to do that, if you were to take a rocket and lift off the Earth vertically, well, what goes up comes down. If you do a vertical liftoff and you don't apply any horizontal velocity, then you'll come straight back down again. So for instance, the Blue Origin New Shepard, that launched to an altitude of some 100 kilometers or so, effectively straight up. But as soon as it's reached its maximum height, it will just fall straight back down, not necessarily exactly where it is launched from, but pretty close to a vertical descent back down to Earth. So the total flight time of Blue Origin New Shepard was something like 10 minutes or so, simply because all it did was go up and then come down. It's the tricky bit, getting the horizontal velocity high enough to put yourself into orbit. That's the tricky bit of rocket science. Okay, let's think about orbits. Now, an orbit is simply the path of an object which is affected by, I've put in brackets there, only gravity. So we should be thinking about the path of an object which is only being affected by gravity. But sometimes we use the term to indicate what's happening to an object that's also being affected by, for instance, the acceleration of a rocket motor. But strictly speaking, an orbit is the path of an object that's only affected by gravity. And I guess we're all used to the idea of planets in orbit around the Sun or moons in orbit around other planets. Kepler observed that the planets orbit in ellipses, and Newton figured out why this was, his law of universal gravitation. In the title there I said Kepler and Newton and Buzz Aldrin, because Kepler made the observations. Newton figured out why, because of the law of gravity, they behave the way they do. But Buzz Aldrin is there because for some reason Buzz Aldrin seemed to have this innate ability to imagine and deal with orbits at a mathematical as well as an intuitive level. His PhD was on orbital mechanics of rendezvous, so perhaps it's no surprise with that amount of training that he was used to the idea of, in order to get from one orbit to another orbit, what do we need to do to get from A to B? So for most of us, that's tricky, mainly because we haven't got it in our heads and the maths is too tricky, but some people are able to deal with that. Newton found that the orbits of planets in the solar system have the shapes of sections through a cone. So if we imagine a cone and we slice the cone horizontally, the section that we make is a circle. If we were to slice through the cone at more of an angle, we would get an ellipse. If we were to slice through the cone at an angle that's parallel with one of its sides, we get a particular shape called a parabola. And if we go to larger angles, then we get a fourth shape called hyperbola. So basically all objects that are moving around in the solar system will follow one of these four paths. Excuse me. Circles, ellipses, parabola and hyperbola. And these curves that describe orbits around the Sun are also the same curves that define the shapes of the mirrors that you might have if you have a reflecting telescope. Spherical mirrors, elliptical mirrors, parabolic mirrors or hyperbolic mirrors are various elements of various types of telescope. The reason that the shapes of orbits are the same as the shapes of mirrors in telescopes is because essentially the maths is the same for telling us what shapes they ought to be. We know that the planets follow closed elliptical orbits. Some of those ellipses are very close to being circular, and we're going to make the approximation of let's ignore the ellipticity, let's just think about circular orbits. But we know in practice that the orbits of planets are elliptical. If an object falls into the solar system from a long way out, like the Oort cloud, if we imagine it starts from essentially zero velocity and falls into the solar system, then it will follow a parabolic arc, as indicated by the red line up there, the parabola. More open than the closed circles and ellipses that we're used to. And if an object comes into the solar system not having dropped in from a great distance at zero velocity, but if it enters our solar system at a finite velocity, then it will follow a hyperbolic trajectory as indicated by this slightly more open line here at the top. So any object that's hyperbolic orbit has entered the solar system at speed, will go past the sun, and if it's not caught by an object in the meantime, will leave the solar system at a similar speed. This happened a little while ago, back in 2017. This object in 2017 came into our solar system, and we observed it passing the orbits of the inner planets as indicated here in August and September of 2017, and it went through perihelion in early September. And by watching this object as it goes past the sun, we can see how fast it's travelling, and using Newton's laws of motion, we can calculate that it must have entered the solar system at speed, and indeed will be leaving the solar system sometime later at a similar speed. So we know that this is an interloper to our solar system. When it comes to orbit size and orbit period, there's something that we need to establish early on so that we can understand essentially all of the rocket science that we need in this particular talk. So let's just imagine a hypothetical situation of a solar system with two planets. The green planet is closer to the sun. If it's closer to the sun, then the gravitational pull is stronger. We don't have to worry about how much stronger. All that matters is the green planet experiences a bigger gravitational pull from the sun simply because it's closer. So remember the cannonball that Newton told us about in Principia? If it's got a strong gravitational pull, it needs to go fast to stay in orbit. The red planet is further from the sun, so the gravitational pull from the sun is weaker, and so the planet can move more slowly and still stay in orbit. So the length of the period of the green planet is relatively short, and for the red planet it's relatively large. And this particular observation, the inner planets always move faster than the outer planets for any two pairs of planets. This is the observation that is absolutely critical for us to understand basically all of rocket science. If the gravitational pull is stronger, the object moves faster. That is pretty much all you need to know to understand rocket science. If we look at how that applies to objects moving around the Earth, this little cartoon shows us that objects moving close to the Earth are moving quite fast, such as the space station and the Hubble Space Telescope. Objects circling at greater distances, like the GPS satellites, are moving more slowly, and objects moving on this outer circle are moving around the Earth once in 24 hours. These are the geostationary orbits. And we can work out exactly how long these objects are going to take to circle the Earth because they're all obeying Newton's laws. Indeed, all of the planets seem to understand Newton's laws implicitly. If we look at the distance of a planet from the sun measured on the horizontal axis, the radius, if you like, of its orbit, let's just think of them as circles for the time being. If we take the distance from the sun in astronomical units, in other words, multiples of the Earth-Sun distance. On the vertical scale, if we look at the orbital period, how long it takes the planet to go around the sun, and we plot those in Earth years. So Earth, of course, occurs at r equals 1, t equals 1. Notice that all of the other planets in the solar system know exactly where they should be. They understand Newton's laws, and they fit absolutely on the line, as you would expect. No need for Einstein's theory of relativity at the sort of level we're looking at here. Maybe if you look in enormous detail at some of the motion of the planets, we might need Einstein, but 99.99% of the time, Newton's gravitation works just fine. If we think of what's happening if we just take a simple model of two objects, how do two objects behave if they are gravitationally bound to each other? In the top left, we see what would happen if we have two objects of equal mass. They would orbit around not one object or the other, they would orbit around their centre of mass, the little red cross there, which is by definition halfway between them if the two masses are the same. If the two masses are different, then they still orbit around their centre of mass, but the centre of mass is now closer to the larger object. So the larger object, the bigger mass object, moves in a slightly smaller circle than the other one. So they still move in circles, but with different radii. If we take that a little bit further, in the bottom left we see two very different masses. Now the centre of mass could, for instance, lie within the larger body. Notice that the red cross is now sitting within the actual size of the larger of the two objects. And if we take that to the extreme, we notice that even a small object like a planet can make a large object like a star wobble, because they are both moving around their common centre of gravity. And that is how some exoplanets have been discovered. We can't necessarily see the planet itself if it's too small and too faint. But if we look at the light coming from the star, look at its spectrum, break it down and see if we can see if there's any shift of the spectral lines towards the red or towards the blue, that would indicate that the star is wobbling. In other words, sometimes coming towards us, sometimes going away from us. If we can see that wobble, then we can infer the existence of a planet going around the star. And we can do that for a number of different planets, and we can work out whether or not the star has a solar system. In principle, that's easy with two objects. Newton tells us exactly how two objects are going to behave. Two objects of essentially any mass, we can work out how they're going to behave, how they orbit around each other. But as soon as we go to three objects, life becomes a little more difficult. Because although it seems very odd, the idea of calculating how not two but three objects move is actually surprisingly tricky. Two-body motion, i.e. the motion of two bodies, one orbiting around the other or both orbiting around their centre of mass, is easily soluble. But amazingly enough, when you have three, it's not just difficult, it's technically impossible. So if we think of, for instance, three objects moving like this, it looks like they're just moving in nice simple ellipses. So surely that's very straightforward. But the more we watch, the more we realise, they're not actually moving in ellipses. It only looked that way to start with. Actually, their motion is completely chaotic. And that is generally true of any so-called three-body problem. It is almost impossible to work out what is going to happen, except in the mathematical situation of very precisely positioned objects where we know exactly what the analytic solution is going to be. Most of the time, if we want to actually work out what three objects in the solar system are actually going to do, the best we can do is a numerical simulation, a numerical approximation of how the objects are going to move. When I talk about these three objects being chaotic, I don't just mean it's a mess, it looks like spaghetti rather than circles and ellipses. A chaotic system is one which we can't predict where the objects are going to be in the future unless we know precisely where they started from. The slightest change in the starting positions or the starting velocities of the three objects would give us ultimately a completely different trajectory, a completely different set of orbits. And generally speaking, the solar system is chaotic. On a long enough time scale, we can't predict exactly where objects are going to be. And that is a little bit of an issue. We always have to deal with approximations. Let's think about orbits themselves and getting from Earth orbit to Mars orbit. How, if we wanted to explore the solar system with spacecraft, how do we get from A to B? If we look at one example, which is the spacecraft called InSight, back in 2018 it was launched from Earth, and this little animation shows us how we get there. You might think that you wait until Mars is as close as possible to the Earth, and yet then you go hell for leather in the shortest distance from one object to the other. But no, the best way of getting from Earth to Mars is to take, rather paradoxically, the longest route. So we follow the pink line here in order to get from Earth to Mars. Earth is on one side of the solar system when we leave, and Mars is on the other side of the solar system when we arrive. It seems to be the longest route possible, but it is the most fuel efficient. It's the easiest way to get there using the least amount of fuel. One thing you notice in this particular way of getting from Earth to Mars, as we approach Mars, Mars is actually catching up with the spacecraft. Mars is actually going faster than the spacecraft at this particular point as they two pass each other. And that's important when it comes to working out how much fuel are you going to need to get onto that trajectory and what are you going to do when you arrive at Mars. So we can see that if we look at it in a sort of plan and just imagine that the orbits are circular. Let's get rid of that, it looks a little too complicated. Let's just pretend that we've got an orbit for the Earth and we've got an orbit for Mars. This is not intended to be to scale, by the way. And let's just assume that they are circular just for convenience. They're actually elliptical. So you can see that what we've got is the Earth where the spacecraft leaves, and we've got the position of Mars when the spacecraft arrives. And notice they are on opposite sides of the Sun. So again, this might not sound very intuitive, but that is the easiest way of getting objects from the Earth to Mars. And the orbit they take is indicated by this blue ellipse. Let me just temporarily remove the other two so you can see it more clearly. This elliptical transfer orbit is called the Hohmann transfer. It is the ellipse that just touches the Earth orbit on one side and it just touches the Mars orbit on the other side. And if we wanted to get out of the Earth orbit and into that blue transfer orbit, we need to give the spacecraft a bit of a kick. We need to go a little bit faster than the Earth is going in order to get onto the blue curve. So a Hohmann transfer, the first thing you have to do is to give a kick with a rocket motor of some kind, some rocket engine, is going to increase your velocity. It will give the spacecraft a so-called delta V, a change in its velocity. And when you've changed the velocity of the spacecraft, instead of circling around with the Earth on the green curve, it's going to enter the blue curve, and it will then transfer its way to Mars. But remember what we said in the previous little cartoon when we looked at the graphic of a spacecraft arriving at Mars. As it gets to Mars, Mars is actually going faster than the spacecraft. So if you wanted to rendezvous with Mars and go at the same speed, you need to give your spacecraft another delta V, another kick, another acceleration in order to get it up to the same speed that Mars is going. If you didn't do that, then if you simply went to Mars and entered the vicinity of Mars but didn't actually accelerate when you got there, then you would find yourself still on the blue curve and you would find yourself coming back on the other half of the Hohmann transfer. Now it might seem that's a good idea. If you decide not to land on Mars, all you do is do nothing and you come back on the blue line. Well, that sounds like a good idea, but when you work it out, you find that it takes about 1.5 years to go round the blue ellipse. It of course takes about 1 year for the Earth to go round the Sun once. It takes a little under 2 years for Mars to go round the Sun. It takes about 1.5 years to do the Hohmann transfer in its entirety. So if you decide to skip a landing on Mars and come back, you end up back at Earth orbit, but it's 1.5 years later. So what's happened to the Earth? The Earth has gone round the Sun once and another half a revolution in 1.5 years. So the Earth is now in the wrong place. If you follow the Hohmann transfer and you come back to Earth's orbit, Earth isn't there anymore. And that's one of the big catches with getting a spacecraft to Mars, especially getting people to Mars. If things go wrong, you can't simply come straight back again because the Earth is in the wrong place. Just as you can only get to Mars when Earth and Mars are in the right position as indicated by this diagram, the same is true when you want to come home. When you want to come home, Mars and Earth have to be in the right place such that leaving Mars gets you to Earth when Earth is in the right place in its orbit. And so when it comes to trying to plan how we get astronauts to Mars, how we land on Mars and how we get them home again, it's always a problem because the timing has to be just right for the Hohmann transfer to work. If you decide not to use a Hohmann transfer, you will need to use a lot more fuel, and that's a problem. The more fuel you use, the more fuel you have to take, the more fuel you have to burn in order to transfer that fuel from A to B. It's a never-ending problem. What about getting to other planets in the solar system? Well, in the 1960s, it was realised that flying a spacecraft close to a planet can effectively slingshot it onwards at higher velocity, a so-called flyby, or its correct name is probably gravity assist, but pretty much everybody calls them flybys or slingshots. So we can explore the outer solar system by picking up more speed by using a gravity assist of planets as we go along. Where do we get the extra speed from? Well, in effect, the spacecraft can rob the planet of some of its energy or some of its momentum. So in a sense, if you were to pick up extra speed as you go past Jupiter, you pick up extra speed, but Jupiter slows down a little bit. So it's a little bit of a trade-off. But how does that trade-off actually work? Because when you think about how things fall towards objects, how gravity works, you might at first sight think this isn't going to work. So for instance, let's take a very simple idea. Let's take a ball on the top of a hill and there's a valley and another hill on the other side. If we just give that ball a nudge, it will accelerate down the hill and its velocity will be highest when it's in the valley, and then it will climb on the other side and it will slow down as it climbs the hill on the other side, and it will end up, if the two hills are the same height, it'll end up just stopping at the top of the next hill. So that's fair enough. We're used to the idea that when you go downhill you accelerate and when you go uphill you decelerate. Well, that's fine. But when you think about it and when you do the maths, you find that at any particular point, it doesn't matter where you choose to do this, if you take 2 points that are at the same height, then the object will be going at the same speed. And of course, like any good physicist, I'm going to ignore air resistance, I'm going to ignore friction, etc. This is purely how much extra speed do you gain by going downhill or uphill. And the answer is whatever you gain coming down, you will lose going up. And at the same height above, in this case, the valley floor, you will have the same speed. So you don't actually gain anything by going down a hill and up again. So if going in and out of a gravity well doesn't gain you speed, why does it work when we're sending spacecraft past planets? Let's just think about that bottom point there where we have maximum speed. If that maximum speed was corresponding to a flyby, let's just pick Jupiter as being one of the most massive planets. So that maximum speed is when the spacecraft is at its closest to Jupiter. So that's the maximum flyby speed. And we can think about the inward speed of a spacecraft approaching Jupiter and the outward speed of a spacecraft moving away from Jupiter. But from what we've just said, the implication is whatever we gain on the downhill leg of approaching Jupiter, gaining from the fact that we're getting closer and closer to Jupiter, whatever we gain there, we will lose on the way out. So our outward speed should be the same as our inward speed, in which case we haven't gained anything. But here's the clever bit. Somebody figured out, well, yes, this idea of whatever you gain with acceleration on the way in, you lose with deceleration on the way out. That is true as seen by Jupiter. In other words, the speeds in and out are the same relative to Jupiter. That's how gravity wells work. But Jupiter is not static. Jupiter is moving because it's, for instance, going around the sun, amongst other things. So if you can arrange it that you come in and you go out on different paths, and you arrange it so that you go out in the same direction that Jupiter is traveling, if you're leaving Jupiter at a particular speed, but Jupiter itself is moving quite fast, then effectively your outward speed is on top of Jupiter's speed. That's how you get the gravity assist. So even though the speed relative to Jupiter is the same in and out, the speed relative to the Sun can be substantially different. And it's not uncommon to have a gravity assist from Jupiter in which the spacecraft is coming in at some 10 kilometers a second relative to the Sun, but it might leave Jupiter at something like 25 kilometers per second relative to the Sun. So an enormous speed boost as long as you get the geometry right. So that's how it works. In 1972, Pioneer 10 used this idea and it left Earth back in 1972, and you see the pink line as it approaches Jupiter in green there. As it approaches Jupiter, there's an abrupt change to the pink line. It changes direction quite abruptly as it passes Jupiter. Not only that, it picks up quite a bit of speed. In fact, it picks up enough speed as it passes Jupiter to leave the solar system. So We're approaching at some 10 kilometers a second, but we're leaving Jupiter at 20 something kilometers a second, which is fast enough to leave the solar system. So Pioneer 10 was the first spacecraft that was given a high enough velocity kick in order to leave the solar system. Pioneer 10 visited Jupiter. Pioneer 11, launched a little bit later, visited Jupiter and Saturn. We wanted to get to Saturn, but the only way to do it sensibly was to go to Jupiter first. Well, no harm there, take a few more pictures of Jupiter. But by going to Jupiter first, you get a gravity assist. Notice that the abrupt change of velocity not only gave it a kick, but it actually sent it across the other side of the solar system. Jupiter wasn't actually in the right place, not in the ideal place at least, in order to go to Saturn. So although it wasn't in the ideal place, it was still worth it in terms of fuel to send the probe to Jupiter first, to give it a velocity kick, to speed it up so that it could then be sent to the other side of the solar system to eventually pass Saturn and get our first pictures of a flyby of Saturn. Whilst flying past Saturn, notice it gets another gravity assist and actually leaves the solar system a little bit faster than Pioneer 10. The same idea was used by the Voyager spacecraft. They were both launched in 1977, actually a few days apart. Voyager 1 was tasked with getting better pictures of Jupiter and also Saturn, and in particular the moon Titan, because that was a target of interest. So again, we leave Earth, we do a flyby of Jupiter, we pick up some extra speed, again that obvious kink there, and then we go flying on to Saturn. But notice that as we pass Saturn, there is no gravity assist, there's no kink in the trajectory there. The intention was that Voyager 1 would fly past Titan because Titan's got an atmosphere. It was considered to be an interesting moon to visit, and so the flyby was designed with priority to go past Titan. And by going past Titan, it missed the opportunity of having a flyby of Saturn itself. That's not that big a deal because that wasn't intended to go anywhere else. Voyager 1's mission was to look at Titan, and it already had enough speed to leave the solar system. But Voyager 2, which was launched a few days ahead of it, but on a different path, Voyager 2 was approaching Saturn some months behind. And because Voyager 1 had already achieved its goal of looking at Titan, it was possible for Voyager 2 to do something different, to fly past Jupiter and get a gravity assist from Saturn and then throw it on to Uranus and then Neptune. Notice that on passing Neptune, it didn't seem to have too much of a gravity assist. What actually happened is it went over the north pole of Neptune and then took a dive below the ecliptic. So a gravity assist at Saturn. See how nicely Saturn and Uranus and Neptune are all lined up. This doesn't happen very often. This was realized in the 1960s that this would be a possibility. And this is why the Voyager program was set up, because of the nice alignment that allowed 4 gravity assists from Jupiter, Saturn, Uranus and Neptune. And the little white ticks on the left-hand side there are just indicating that Voyager 2 has actually gone below the level of the ecliptic. Everything up to that point was essentially in plane, but when going over the north pole of Neptune, it gave it a little bit of a kick and ended up diving below the plane of the ecliptic. If we have a look at how fast Voyager 2 was going, if we plot out as a function of its distance from the Sun in astronomical units, if we plot its speed relative to the Sun, then it started from Earth at about 36 kilometers per second, and that speed dropped, but then was given a kick by Jupiter, a kick by Saturn, and then again by Uranus, and then again by Neptune. Notice that there's always a kick there, but notice that the Neptune kick, it got very fast as it flew by Neptune, but notice how much it dropped as it left Neptune. It actually ends up leaving Neptune actually at a lower velocity than it arrived at. So in other words, it wasn't so much a gravity assist, it was actually a slight slowdown. But that doesn't particularly matter. They did that because they wanted a maneuver that went over the pole of Neptune to get a better view of the planet. Losing a little bit of speed there was not an issue, because if we look at how much speed do you need to leave the solar system escape velocity, indicated in the blue line there, you see that as Voyager approaches Jupiter, it hasn't got enough speed to leave the solar system. But the kick from Jupiter is large enough, because Jupiter is a big planet and you tend to fly by Jupiter fairly closely. That kick is large enough to give you an escape velocity. The red line is above the solar system escape velocity blue line. Not only that, but the kicks you get from Saturn, Uranus and Neptune aren't strictly necessary to leave the solar system, because the red line stays above the blue line throughout. And the fact that we actually lose a bit of speed at Neptune is not that big a deal. The idea of using gravity assists might make a certain amount of sense. The idea that you can use Jupiter to send you on to Saturn, and then you get another kick which gets you to Uranus even faster, and then you get another kick which gets you to Neptune even faster. That all seems very sensible. What is perhaps not so obvious is that gravity assists are also used to visit the inner planets. So for instance, Bepi Colombo, on its way to Mercury, launched in 2018, you see on the right hand side here, it actually had a flyby of Earth to lose some speed, and then a flyby of Venus to lose a bit more speed, and then a second flyby of Venus to lose a little more speed, and then a flyby of Mercury. And for the next few years, it's going to be doing more flybys of Mercury to lose speed. So I'm not going to talk about the geometry, but instead of flying past a planet and leaving it in the same direction that the planet is moving, if you were to move it in the opposite direction, you would effectively add to the planet's velocity, but lose some of the velocity of the spacecraft. And you need to do that if you're falling into Venus orbit or Mercury orbit, because if you didn't do that, you would be moving far too fast, and you would need fuel in order to slow down. And regardless of whether you're using a flyby, a gravity assist, in order to gain velocity or to lose velocity, in order to accelerate or to decelerate, it doesn't really matter. In both cases, you can change your velocity without using precious fuel. And that's why gravity assists are used. You can always have an alternative if you've got a large enough rocket motor and enough fuel. But every kilogram of fuel you take means that you've got 1 kilogram less of instrumentation for you to measure what it is you want to measure when you get to your target planet or asteroid or comet, whatever it happens to be. In some cases, you want to get to a planet and you don't want to go into a simple orbit like Cassini around Saturn didn't go into one orbit and stay there. It wanted to see the planet, and in particular the ring system, from various angles, from various aspects. And so Cassini continually changed its orbital pattern. But in order to do that, it needed to use fuel. And you can see just how complex the orbits are. If you just spin the whole structure, you see it's changed its orbit many times in order to get different distances and different angles relative to the planet and the ring system. But the downside is your mission will be compromised if you run out of fuel. If you require fuel to change your orbit, then you've got to take enough fuel with you, and when your fuel runs out, your mission is effectively over. And that's something I'll come back to right at the end. So let's think about the final aspect of rocket science. One of the most confusing things is, how can you park at a place in space where there is nothing? The idea of going to Saturn and going in orbit around Saturn is something we can get our heads around. But how can you go to a point in space and orbit there even though there is nothing there? So what are these Lagrange points all about? Let's come back to the basic idea. This is so important, it's worth showing again. Remember the idea of two planets going around the sun. If the green planet is closer to the sun, it feels a stronger gravity. If it feels a stronger gravity, it moves faster. And even though it's on a smaller orbit, it's moving faster, and so of course it takes much less time to go around the sun. The red planet, the red object, whatever it may be, is further from the sun and it has a weaker pull, and therefore it goes more slowly. This is the fundamental point I'm trying to make. A stronger gravitational pull means that for orbits to work, you have to move faster. So we're now going to use that to understand Lagrange points. So we can imagine the gravitational pull on the red object and the green object are indicated by the arrows there. The red object is further away, so the gravitational pull is weaker. Greater distance, less force. And we can ask ourselves, is that always the case? Well, if we're only considering the pull of the sun, yes. We can't change the gravitational pull of the sun, so if you're further away from the sun, the gravitational pull of the sun will necessarily be less. But we can arrange it so that one object feels an additional gravitational force, not just the force of attraction of the sun. So let's think of a situation where, let's imagine the green is the Earth and the red is an object of some kind. So the Earth is going around the sun with a period of exactly 1 year by definition. Let's imagine that we have a red orbit which is outside the orbit of the Earth, and that of course will have a period of more than 1 year. If it was Mars, it might be a period of nearly 2 years. But let's imagine a red orbit which is a little bit closer to the Earth orbit. What if the red orbit was close enough to the Earth orbit so that the object, the red object, is not only pulled towards the sun, but what if it's also pulled towards the Earth as well? In other words, the red object is pulled, as indicated by the yellow arrow, towards the sun, but also a smaller green arrow is pulling it towards the Earth. Now, we're not going to go through the maths, but there is a red orbit which is at just the right distance such that the extra pull from the Earth means that the red object moves around the sun faster than you would expect. Instead of taking more than a year, it is possible to find an orbit where it takes 1 year. In other words, the red object will move around with the green object. The red object is always being pulled towards the sun, and it's also being pulled towards the Earth because they are both going around together. That is the basic idea of a Lagrange point. It's not a fixed point in space. It's a point in space which moves around the sun in step with the Earth. And therefore, as seen from the Earth, it looks like it's a point in space which isn't moving. But it is moving around the sun in the same time it takes that the Earth goes around the sun. And that is precisely what we mean when we talk about one of the particular Lagrange points called L2. On the right hand side there you can see I can simply replace the red object with a point which I've labelled L2. L2 is being pulled towards the sun, and it's also being pulled towards the Earth, and that extra bit of gravity means that L2 goes round the sun in 1 year. Now bear in mind this diagram is a little bit misleading because the distance from the Earth to the Sun is 1 astronomical unit by definition, and the distance from L2 to the Earth is not as large as I would indicate in this diagram. So the distance from L2 to the Earth is about 1/100th of an astronomical unit. So this diagram is quite definitely not to scale. I've simply exaggerated the size of the red orbit in order to make it a little bit clearer. Now the concept is exactly the same for another Lagrange point called L1. This is a point inside the Earth's orbit. So L1 is closer to the Sun, so you'd expect L1 to go round the Sun faster than the Earth goes round. But notice that L1 is being pulled towards the Sun, but also the Earth is pulling it in the opposite direction. So the actual gravitational pull on any point at any object at L1 is actually less than the pull you would expect purely from the sun, and hence L1 goes around the sun in 1 year. And it's the same for the other Lagrange point, which I'm going to mention shortly. They all go round the sun in 1 year. And again, this particular diagram is not to scale. Earth to sun is 1 astronomical unit. The distance from L1 to the Earth is about 0.01, 1/100th of an astronomical unit. In other words, L1 and L2 are roughly speaking the same distance from the Earth, one on the inside track, one on the outside track. So L1 is a good place to put spacecraft that will observe the sun, because you can effectively park a spacecraft there. It'll go around the sun in 1 year, and it will always have an unobstructed view of the sun because the Earth will always be behind it and the sun will always be in front of it. Unlike an object which is orbiting the Earth, in which case you will get the Earth in the way every once in a while, just like the Hubble Space Telescope can't fixate on one point in the sky because every half a rotation the Earth gets in the way. At the Lagrange points, you don't have that inconvenience. So we can work out where the Lagrange points are because Newton tells us that gravitational force between two bodies simply falls off as the square of the distance between them. So if we want to calculate where in space do we have to be in order to go round the Sun in 1 year, where are the L1 and L2 points, we can just use Newton's laws of motion and the fact that gravity falls off as 1 over r squared. And there's the formula, and we've got the mass of the Sun, mass of the Earth, and we just solve for r. Simples. Everybody can do that before breakfast, I'm sure. Okay, I admit that I said early on it's not that hard if you ignore the maths, so I suppose we're going to have to ignore the maths and just say it can be done. People can work out where these Lagrange points are, and it turns out there are 5 of them. I've mentioned L2 and L1 on the right hand side there. Notice there's an L3 point which is on Earth's orbit or very close to Earth's orbit on the opposite side of the Sun. There are no plans to put spacecraft there because why would you? Anything you place at L3 you instantly lose communication with because it's on the other side of the Sun, and so you can never actually see it. L4 and L5 I'll come back to shortly. But if we were to place an object, a spacecraft, at L2, why would we want to do that? Why is L2 such a useful parking place for spacecraft? Well, one of the big advantages is that you can place an object there with a sun shield which can block out all of the light or the heat from the Sun and the Earth and the Moon because they're all on the same side of sky. In other words, your spacecraft can look out away from the Sun, and everything that you don't want to look at, the Earth, the Moon and the Sun, is on the other side, and a single sun shield can block all of that in one go. That's what Gaia did when it was placed at L2, and more recently that's what the James Webb Space Telescope has done with its large sun shield, which is blocking the heat from the Sun and the Earth and the Moon. So there's a good advantage to placing yourself at L2. Strictly speaking, it's not at L2. L2 is a point in space that obeys the rules that I've shown you up till now. L2 is actually in Earth's shadow. As you can see here, it's on the line from the Sun to the Earth. Ignore the Moon for the time being. It's on a line from the Sun to the Earth and then L2. So L2 is actually close enough to the Earth, being only 1 million miles or so, maybe 1.5 million kilometers, some 4 times further away than the Moon. But the Earth is 4 times bigger than the Moon, which means that the Earth's shadow does stretch that far. So if you were to place an object at L2, then actually the Earth would eclipse the Sun. So if you wanted to have solar panels that charge, you wouldn't place something at L2. So what you actually do, as indicated in this little cartoon on the right hand side, is you would actually place the spacecraft in a small orbit. Well, not necessarily that small, but you would place it in an orbit around L2. And indicated by these arrows here, if the spacecraft drifted away from L2 in this direction, then the Earth's pull will tend to pull it back again. And if it drifted away from the L2 point in this direction, the Earth's pull would tend to pull it back again. In other words, it's self-correcting. In terms of in this diagram, the vertical drift, it will always tend to end up coming back to L2. Or if you wish, you can always go into orbit and you can always have what looks like a pull towards L2. It's just the pull of the Earth. So the pull of the Earth always brings it back in that direction. But if we look at the other directions, what happens if the object drifts towards the Earth, or what if it drifts away from the Earth? Well, there is nothing to bring it back to L2. If an object placed close to L2 starts to drift towards the Earth or away from the Earth, it will continue to drift towards the Earth or away from the Earth unless you do something about it. The ability to park something at L2 is visualized in some cases by this rather odd-looking donut. If we imagine these contours represent contours of height and think about an object that wants to roll downhill, we can get an idea of whether a spacecraft wants to stay at a Lagrange point or not. So let's look a little more closely about what's going on around L2, and let's ignore the other Lagrange points just for the moment. So these contours, remember, we imagine them as contours of height. So it's high in the top left and bottom left, and it's low on the right hand side. So the arrows give you the direction of downhill in the vicinity of L2. If we were to place an object close to L2, which way would a ball want to roll? And the argument is that downhill is in this direction, in this vertical sense. So an object will tend to roll towards L2, but if it rolls this way, or if it rolls that way, then it will roll away from that particular point. So L2 is not a hilltop. If it was a hilltop, downhill would always point away from L2. L2 is not a gravity well. It is not a well in the sense that that would mean that all the arrows would have to point towards L2. It's not that either. 2 arrows point away from L2, 2 arrows point towards L2. So it's not a hilltop, it's not a well, it's a saddle point. And a saddle point is one that has this particular property that 2 downhills are pointing away from L2 and 2 downhills are pointing towards L2. So a mathematician would represent it by that mathematical function in the bottom right hand side. Everybody else would just say it's a Pringle. So one of the take-home messages here is the James Webb Space Telescope is parked close to a Pringle. And so if we think about what's going on there, we can put the James Webb, or indeed Gaia, into a little orbit. The Earth will keep pulling it towards L2. However, if it drifts towards the Earth or it drifts away from the Earth, then we will need to use a little bit of fuel with our station-keeping motors to give it a nudge. And it's been calculated that it's been placed close enough to L2 that it won't drift towards Earth very quickly, and it should only need the smallest of nudges every few months just to keep it in position. In fact, when it was launched and when it was placed at L2, it was placed at L2 with such exquisite precision that they've managed to save a lot of fuel. And given that the lifetime of the James Webb is not dictated by the instruments themselves, it's not keeping the instruments cold that's going to dictate the length of time James Webb can operate. It's how often it can keep nudging to keep itself in orbit around L2. And by positioning itself closely to L2, it didn't need to use much fuel in terms of making corrections to arrive at L2, which means it's got plenty of fuel left to make these corrections every few months to just nudge it and keep it in position at L2 or as close as possible to L2. What about these final 2 that I haven't mentioned yet, L4 and L5? Well, there are some objects there, but not in Earth's orbit. If we again think of this particular donut, then we wouldn't expect too much to exist at L4 and L5, especially if the Earth doesn't have a particularly large mass trying to keep things there. So in principle, things could orbit around the L4 point or orbit around the L5 point. It's a little bit different than the orbits around L2, and we're not going to worry about the details. But the Earth's gravity isn't really strong enough to hold any objects in those positions. But Jupiter's gravity is strong enough such that objects have started to collect at L4 and L5. And these are various asteroids that have been collected over billions of years, the so-called Trojan asteroids, of which there are quite a few. They don't just sit at L4 in any more of a sense than the James Webb sits at L2. They actually undergo little orbits as indicated by these sort of contours on this donut that I showed earlier. But as well as objects sitting at those Lagrange points, this particular donut also indicates to us that there can be some very, very odd-looking orbits that exist around systems such as planet and sun. As well as in principle collecting objects at the Lagrange points, it's also possible for objects to orbit in really weird-looking shapes. So this looks like it shouldn't really work, this large horseshoe-shaped objects. They look really weird, but actually they still obey the rules. In other words, if you imagine what would happen for an object here Well, an object in this position indicated by the cursor will be pulled towards the Earth, which tends to pull it a little bit closer to the Sun. But remember what happens when you get closer to the Sun? The gravity is stronger, so you go faster. So you're going around the Sun faster than the Earth goes around the Sun. And remember, the Earth is going around the Sun in 1 year. So an object closer to the Sun will actually go round a little faster than the Earth, and eventually it'll catch up with the Earth. And when it does that, it catches up with the Earth. What is the Earth going to do? The Earth pulls on it and tends to pull it to a slightly higher orbit. What happens if we go to a higher orbit, further from the Sun? If we're further from the Sun's pull is less, so we go a little more slowly. So we're still going around the Sun, but we're no longer going round in a year. So the Earth is now gaining, and we start to lag behind the Earth, and we follow this arc, and we end up back where we started. So objects can go round this large C-shaped or horseshoe-shaped orbit. It looks weird only because we're looking at it as if it was a static system. We have to remember that the Earth is going around the Sun in 1 year, and we're looking at the positions of objects relative to the Earth. We have to imagine the whole thing turning at the rate of 1 revolution per year. And then horseshoe orbits start to make a little more sense. So the idea of closer to the Sun they move faster, further away from the Sun they move slower, again is really all we need to understand about why these horseshoe orbits exist. But before we leave orbits, perhaps the weirdest orbits of all are those that are not closed loops. So I guess we're used to the idea of circular orbits or elliptical orbits, which, depending on how you look at them, might look a little bit like a horseshoe if they move relative to the Earth. But there are some orbits that are not closed and don't seem to make any sense whatsoever. And this is another example of a three-body problem. Remember, three-body problems are generally chaotic, but it is possible to find solutions which look very odd if we place 3 objects very carefully and let them go and let gravity do its stuff. 3 objects of equal mass. If we place the objects there and then ask what happens when gravity is allowed to pull them together, the result will probably surprise you. They fall towards each other, and then they slow down and stop, and then they retrace their tracks again. So none of this motion is circular, elliptical, horseshoe. It's not even a closed system, but this is precisely what would happen if you start those 3 objects at precisely the right point. And that, of course, is a really big if. At the bottom there it says, is it possible for stars in a triple system to move that way? Well, the answer is yes, if the 3 stars were exactly the same mass, and if they started at precisely those 3 positions with 0 velocity, then you'd expect them to behave like that. But reality is that you'll never get 3 objects with the same mass, and you would never make a star system where the stars started out at 3 different positions with no relative speed. When stars are born and planetary systems are born, they are always the result of accretion, and there's always motion there. So mathematically that's very interesting, but we wouldn't expect ever to observe orbits like that. And when we're talking about orbits that we're not likely to see, well, basically, don't get me started when we're talking about black holes. The space around a black hole is so warped and so distorted, we can't expect Newton's laws of motion to tell us about how objects are going to behave. We're not expecting to get circles and ellipses when space is so warped around a black hole that basically all bets are off. So I've told you a little bit about what rockets do, about the nature of orbits, how we change orbits to get from Earth to Mars or Earth to the outer or indeed inner solar system. And I've told you a little bit about how Lagrange points work by sort of skipping the maths and just saying all you need to do is understand the basic principles. So why is rocket science considered to be so hard? Why does everybody say, well, it can't be that hard, it's not rocket science? Well, it's considered hard because, yes, there are some objects in the solar system that move in ways that are not, at first sight, rather intuitive. For instance, the horseshoe orbits. We can understand it, but it's not obvious at first sight why they behave that way. And yes, when it comes to calculating how to put the James Webb Space Telescope into orbit around L2, that's not a trivial mathematical problem, especially when you think of the phenomenal accuracy that they actually achieved. But the underlying principle, the underlying idea, as I've said time and again in this talk, is very straightforward. Stronger gravitational pull leads to faster motion. And the easy way to remember that is to remember that the Earth moves around the Sun faster than Mars moves around the Sun. And you could argue, slightly tongue-in-cheek, but you could argue that all of rocket science is based on that fundamental idea. That's all there is to rocket science. Just remember that stronger gravitational pull leads to faster motion. Everything else that you read about rocket science, all of the details, that's just maths. After all, as they say, it's not rocket science. Thank you for listening.